In this video, we'll learn how to perform text mining using Weka. So Weka is a software which can be used for data mining. It stands for Waikato Environment for Knowledge Analysis. It's a free software developed by the University of Waikato in New Zealand. So let's get into understanding of the dataset. So here we have the dataset, and the dataset contains two folders, business and sports. The business folder contains 400 text files. So let me show you one text file, for example. So this is how each of the text files look. So we have 400 of them. Going back, we have sports folder, and even in this we have 511 text files. So for example, this is how one of the text files in the sports folder looks. So this is the dataset that will be loading into the Weka software to perform data analysis and text mining. So here I have opened the Weka software. So this is the Weka GUI chooser. Here we can see in the right hand side that we have four applications. One is Explorer, Experimenter, Knowledge Flow, and Simple CLI, which stands for Command Line Interface. We will be requiring the Explorer application, so just click on it. And then so this is a Weka Explorer where we'll be loading in the data set. So here you can see that there's a button called Open File. Click on that and navigate to the folder. So here I have the folder which is called Weka Dataset. Just click on Open. Initially you will get an error that Weka is not able to understand the kind of folder that's been selected. Just hit on OK, and here we will get an object editor where we can choose what kind of text loader is required. So click on choose, and since this is a folder which is containing text files, so we need to choose text directory loader and click on OK. So within a few seconds you'll be able to see two attributes here. The first attribute is called text and the second attribute is called class. So when you click on class, in the right hand side you can see that there are 400 instances in the business class and 511 instances in the sport class. So as I had already told, in the business class we had 400 text files, so we have 400 as the count here, and in the sports folder we had 511 text files, so that's the reason we have 511 as the count here. And below you can also see a visual representation of the distribution of the instances among two different classes. So 400 for blue and 511 for red. So you might be wondering, where is all the text that was in the text files? Why is it not being visible? So when you click on text attribute and here you click on edit, you'll be able to see that we have two columns. One is text string and the other is class. So here in the class we have business and sport, but each of the text file has been concatenated as a single long string. But if it's present like this, when we build some machine learning models for data analysis and text mining, the model will not be able to understand the kind of text that's present. So we need to convert this long string into attributes and value pairs. So let's get into the process of doing that. To convert this entire big string into attribute and value pairs, we need to apply a filter called string to word vector. So here below filter, click on choose, expand filters, go to unsupervised, go to attributes, and then scroll down where you can find string to word vector. Select that, and here click here. Now here you can see a lot of properties that you can select for this filter. So let me go over some of them so that you get an understanding of what they actually mean. The first here is called IDF transform. It stands for inverse document frequency. It's a boolean attribute. You can set it to true or false. Next we have TF transform, which stands for term frequency transform. Again you can set true or false. So when you set both TF transform and IDF transform to true, you'll be getting TF IDF metric as the attribute value, which stands for term frequency inverse document frequency. And you can also convert all the words into lowercase. So for that you can set lowercase tokens as true. And then we have another attribute or property called minimum term frequency. So when you set this to 1, each of the words occurring will be considered as attributes. But for instance, let's say you set it as 5, only if each of the words has occurred at least 5 times in the entire dataset, those will be included as attributes. Now you can also normalize the data. Here you can normalize in the entire data or only the test data. You can choose either of them. And then you can also select output word counts as true if you want to output the word count. So by default, if you have output word counts as false and term frequency transform and IDF transform as false, the attribute value will be a boolean number, so it's either 0 or 1. And if it's 1, it indicates that this word has occurred in the text file. If it's 0, it indicates that it hasn't occurred. So if you want to get rid of the boolean metric and come up with a number, then you can select this as true. So let's say a word occurs 2 times in the entire data set, then the attribute value for that word will be 2 if you set this as true. Now you can also choose a stemmer here. So here we have low wind stemmer or snowball stemmer. So if you don't actually know, stemmer will stem all of the words to their root form. So let's say we have a word called having, and when you use a stemmer, the output will be have. So it will convert all of the words to the root form. And by default, the Weka software has a list of stop words which has been selected by default. And you can also select a tokenizer. So a tokenizer is able to decipher words and tokens. So here we have 2 options, n-gram tokenizer or word tokenizer. Word tokenizer is the default, and I recommend you to leave that as it is. And here there's an attribute called use stop list. When you set this as true, all the words which are present in the stop list by Weka will be ignored as attributes. But if you set it as false, even the stop words will be included as attributes once you apply this filter.
So with the help of these attributes, what we can do is we can compare the effect of one property of this filter with the help of machine learning models. So what I mean is, let's say we run a decision tree classifier with TF-IDF transform and without TF-IDF transform. Then we can compare the performances by using some training splits and then come to a conclusion what is the effect of TF-IDF on this particular dataset. So for that, first we will create one dataset where we have the TF-IDF transform. So I'm setting IDF transform to true and TF transform to true. And I will also lowercase all the tokens, so I'll be setting this lowercase tokens attribute to true. Then I will also set output word counts to true because we want a numeric value rather than a boolean number as the attribute value. And for stemmer, I'll be using low wind stemmer. Any of the stemmer can be used. And for tokenizer, I leave the default, and the use stop list, I will make it true. And then click on OK. So now we need to click on apply here. So you can see at the bottom right, the bird is moving right and left. And now it has stopped. So which means now that this filter has been applied to the dataset. So initially we just had 2 attributes, but now you can see that the count here is 1569. So in total we have 1569 attributes and 911 instances. So what we can do is we can go ahead and save this dataset and all the filter that we have applied so that we can later use this in the model building stage. So for that, just click on the save button here and then go to desktop or the location you want and just rename the file as applied filter with TF-IDF and hit save. So now you will have this pre-processing step saved as an ARFF file. So ARFF stands for Attribute Relation File Format. It's a format used by the Weka software to store the pre-processing done inside Weka. Now what you can do is just click on undo here. So now we'll be back with the same 2 attributes. Just go for this filter and here make IDF transform to false and TF transform to false. So now we don't have TF-IDF applied to this dataset, but all the other properties kept as it is. So by keeping all the other properties same, we are essentially being able to see the effect of TF-IDF on the dataset. So here low and stemmer is as it is, and then use stop list has been set to true. So now click on OK and hit apply. Now within a few seconds this filter will be applied. You still have the same number of attributes, but the attribute values will be different. You can just click on any of the attribute and then in the right hand side you can get a statistical information of the attribute. So you can see like minimum is 0, the max is 4, the mean is 0.03 and the standard deviation is 0.22. Now just go ahead and save, go to the location, then here instead of with, just make it without TF-IDF and then hit save. So now we have 2 ARFF data sets, and then we can build machine learning models with both of these 2 data sets that we have saved and then compare the performance of TF-IDF, which has been the interest for this pre-processing step. Now, before going ahead with building the machine learning classifiers on these two datasets, I want to take a step back and look at the class distribution. Because in most of the real-world datasets, the classes are imbalanced. That is, there is an unequal number of samples in each of the classes. So here, click on the class attribute, and then in the right-hand side, you can see how the number of samples is divided among the two classes. Here, there's a significant difference between the number of samples in each class, which is 400 and 511. So I want to consider balancing the classes before going ahead with the model building stage. So now you can balance the classes in two ways. One is oversampling and the other is undersampling. In oversampling, you increase the number of samples in the minority class. That is, you oversample the minority class. The second way is undersampling, where you just select few samples from the majority class, and that number should be equal to that in the minority class. So now for this demo, I'll be going ahead with the undersampling method. So for that, what we can do is apply a filter. So here, click on choose, go to supervised, go to instance, and here you need to select spread subsample filter. This is the filter which is used for undersampling. Just click on the filter, and here you see an attribute called max count, which indicates how many number of samples do you want in each class. So here, since the minority class has 400 samples, I even want the sport class to have 400 samples. So here, just enter the number as 400, click on OK, then hit apply. Now within a few seconds, you'll be able to see that there are 400 samples in both of the classes. Now the classes are balanced. So we can go ahead with the model building stage. For that, you need to navigate the classify tab. Then here you can choose a classifier. Here is the test options, where you can evaluate the performance of the classifier using cross validation or a percentage split, or you can also supply a test set explicitly. So here, let me choose a classifier first. I'll go ahead with the decision tree classifier. So here, expand the trees folder, and the code that Weka uses for decision tree is J48. That is the nomenclature. So now this decision tree classifier has been chosen. We will now specify a percentage split for evaluating the model. So let's say 10%. So 10% of the entire data set will be used for training, and the remaining 90% will be used for testing. So this is just for demo purpose. I know that the standard distribution among train and test sets is 80:20, so we'll come to that. And to build a classifier, just click on the start button, and you can see at the bottom right the code is moving, which means the processing is going on. Within a few seconds, you can see that the classifier output window is being populated. So just scroll above. So here you can see that 800 instances are there, 1569 attributes are there, and 10% of the dataset is being used for training, and the remainder is test, so 90% for testing. And you can see that there's a prune tree. So if you don't know what is pruning, so pruning is a method where you cut down some branches to prevent overfitting. Now you can also see the decision rules that the model has built here in the diagram, and if you scroll down, you can see some information about the tree. You can see that 23 leaf nodes are there, and 45 is the length of the tree. And you can also see that only 6.06 seconds were taken to build this model, and 606 instances were correctly classified and 114 were incorrectly classified. So the accuracy of this model is 84.17% for 10% split. And you can also see the other metrics like mean absolute error, root mean squared error, which are the standard metrics in evaluating any machine learning models. Here you can also see the detailed accuracy by class, that is recall, precision, true positive rate, false positive rate, the confusion matrix, ROC curve area, that is AUC, ROC, and so on. And here you can also go ahead with a naive Bayes classifier. So just expand the base directly and select naive Bayes. Now let's say you want to train on 80% of data, so just specify 80 here and click on start. So within a few seconds, you will see that you get the performance of the model. So we can see that 99.37% is the accuracy of naive based classifier. In Weka, we also have another option of setting a random seed. So if you got more options here, you can see the random seed value is there. So by default it's 1. So now let's change it to 2 and click on OK. So what happens now is we get a different training and test set. So running the same model for the same percentage split more than once is very important so that you get an accurate estimate of the performance. Because if you just take one random seed for one split, then you might get a biased performance. That is, the way the samples are being distributed among train and test sets can determine the performance. So you can run the same split for more than one seed and then just take the average. So let's run this classifier again. So here we can see that the performance has remained the same, but one metric has differed, which is relative absolute error. So initially it was 1.2452 and now it's 1.25. So here for naive Bayes it doesn't make much difference, but with other classifiers it makes a significant difference. And you also have the option of choosing a support vector machine. And you know that for a support vector machine it's very important to determine the right kernel and the right kernel parameters and the cost parameter. So initially what we do is, first let's go to the meta directory and then click on grid search. So what this method does is it finds the best values of the parameters for this given dataset. So just click on this. You can see that we have a lot of parameters for the grid search filter. So using grid search we can find the optimal cost and gamma values. So here if you see that we have X variable and then the Y variable. So X variable is for the cost. So here in X property we will write classifier.cost. And then in the Y property we will write classifier.gamma, as we're looking for these two values. And let's say the range of values that grid search has to search for both cost and gamma is 10 power minus 2, that is 0.01 to 10 power 5. So the base will be 10 and the maximum will be 5 and the minimum power will be minus 2. Same goes with gamma. So the maximum is 5 and the minimum is minus 2. And the expression will be power of base comma I, which means it's base to the power index. So we essentially want the range of values to be searched as 10 to the power x. So here the x ranges from minus 2 to 5. So we set the x expression as power of base comma I. Now we need to choose a classifier here. Since we are optimizing the parameters for a support vector machine, just choose libsvm. Libsvm is the nomenclature for support vector machine in Weka. And just click here. And it's very important to normalize the data set. So just set normalize to true. And here we can choose the kernel. So here when you click on kernel type, you can see we have the linear kernel, polynomial, radial basis function, and sigmoid. So you can repeat the grid search procedure for each of the kernel. So let's say first I choose radial basis function and run this grid search. I'll be able to get the optimal parameters for the radial basis function. But if I want the optimal parameters for linear kernel, I need to choose linear and then run the whole grid search procedure again. So first I'll go ahead with the radial basis function and normalize by setting normalize to true. Click on OK. And here we need to modify evaluation to accuracy, as that is the metric we're aiming for. And we don't want to apply any filter, so just set filter to all filter. And now you can click on OK. And then you can specify percentage split, so I'll go with 2/3, which is 66%. Then click on start. Now grid search is a procedure which takes a lot of time because it has to go through multiple parameter settings. So it can take sometimes just 5 minutes, or it can also go up to 10 minutes. So just bear with it. And once it's done, you'll be able to see the optimal parameters here in the classifier output window. I would also like to give you a tip. So my tip is to run grid search procedure twice for each kernel by using a different random seed. so that you get an accurate estimation of the performance. So in total, you'll be running the grid search procedure 8 times, 2 times for each kernel, and since there are 4 kernels, 4 times 2 is 8. Now let's say you found out that Gradle basis function gives the highest average performance with both the random seeds. Now what you can do is, you can just choose the classifier, go to functions folder and click on libsvm. That's the nomenclature for support vector machine. And here in the classifier output, you would get to know what are the optimal parameters for cost and gamma, which gave that highest performance. So let's say for cost it was 10 power minus 2, so 0.01, and for gamma let's say it's 10 power 3, so it's 1000. So kernel type, set it to Gradle basis because that gave the highest performance, and also set normalize to true because normalization is very important in support vector machine, because this classifier considers distances as an evaluation metric of how the support vector machine is designed. So if the data is not normalized, the difference in the magnitudes of two different values can give a significant impact of their distance. So just click on OK and then click on start. You can specify any percentage split that you want, then let the procedure run, then you'll get the classifier output. So here we got 47% as the accuracy. Now in your case you might have gotten some other parameter combination which gave the optimal highest accuracy. You can go ahead with that. So this is how you perform text mining using Weka. Let's say you have evaluated and built all the models on the dataset with df-idf. Now just repeat the same procedure again on the dataset without df-idf. Remember that we had created 2 ARFF datasets in the initial pre-processing stage. So once you get the outputs from both of the datasets, now you can compare the performances and then understand, is support vector machine's performance better with df-idf or without df-idf? If it is with df-idf, by what amount is it better? Is it a significant improvement? And which of the 3 classifiers gives a significant improvement? So here, without running or writing any code, you're able to execute machine learning models, execute data pre-processing, build the data sets, and so on. So Weka is an awesome software for data mining and text mining. Thanks a lot for watching the video. Make sure to hit that like button and subscribe. Turn on the bell notification so that you get notified of my every video. Make sure to subscribe to receive more awesome data science videos and practical knowledge from the real world projects that I do, which will be very helpful because data science requires a lot of practice and implementation so that you understand the concepts well.